Hey geometry students, I am going to walk you through lesson 2.3. We're on page 46 of your student journal. All right, so there's actually only there's only one vocab, but then there's some postulates and stuff that I want to go through today. So the first vocab just says a line perpendicular to a plane. Pretty self-explanatory, but what I wanted to say to you about that is it only occurs, so I'm going to write this down. So it occurs, oops, that's supposed to say only if the line intersects the plane in a point and is perpendicular to every line in the plane that intersects it at that point. So that's kind of a long definition. So basically, it occurs only if the line intersects the plane in a point and is perpendicular, that's the symbol for perpendicular, to every line in the plane that intersects at that point. So think about that one for a second, right? So it only occurs if the line intersects the plane and it's perpendicular to every line. So it has to be perpendicular to every line that intersects the plane at that point. And that's pretty much just kind of the main definition of that. So I just kind of wanted you to get a visual of that one. All right, so there's quite a few postulates in this section, and I want to make sure that we understand, or at least kind of walk through all of these actually. So the first one is 2.1, two-point postulate. So today in our activities, we're going to have you kind of like identify which postulate is which. Normally we don't have you memorize the postulates, but we're asking you to kind of understand them. So the two-point postulate basically just states that through any 2 points, there exists exactly one line. And so what they're giving you an example of here is, here's line AB. If you have 2 points, you can draw a line through it. So again, remember, a line's infinite, it goes on forever in both directions. Notice you can also call this line L, or you can call it line AB or line BA. So there's a couple different options here. The next one says line point postulate, and these are very closely related. They're kind of like the opposite. So a line contains at least 2 points. So a minimum, obviously a line, since it's infinite, would contain infinite number of points. But in order for us to draw the line, we need to have at least 2 labeled points, which is why when we do our symbols for lines, always either do A to B, like in this example, or B to A. We use 2 points, so we use those 2 letters, and we name the line through it. And so that's why we don't use 3 or 1 or whatever. You need at least 2 points to be able to kind of label it as a line. Next one, 2.3, line intersection postulate. If 2 lines intersect, then their intersection is exactly 1 point. So a lot of these are more common sense, right? So what we're talking about here is 2 lines that intersect. Think about like solving a system like you did in Algebra 1, right? So 2 lines intersect, there's 1 point at which they intersect. And so in this case, line M and line N intersect at point C. The next one, 2.4, is 3-point postulate. So through any 3 non-collinear points, there exists exactly 1 plane. So again, let's kind of unpack this one a little bit. So non-collinear means they're not in a straight line. So if we have any 3 points that are not necessarily in a straight line, then we can call them on the same plane. So unlike a line, we need to have 3 points to name a plane. So like we would name this plane, plane DEF, for example. Or plane R, or plane R, we could call it that, right? Because it's just the name of the plane. So there's a couple different options here. But we need to have 3 points to name a plane, and then you need only 2 points to name a line. And then kind of going along with that basically just says a plane contains at least 3 non-collinear points. So again, kind of more the converse of that, the opposite of that. So there's some more postulates on the next page. So let's walk through these. And you can see these are pretty self-explanatory, right? Like they're kind of using our definitions that we've talked about in the past. So this one is 2.6, says plane line postulate. If 2 points lie in a plane, then the line containing them lies in the plane. So basically we're kind of doing a combo here. We're talking about the 2 points make up a line, but then if those 2 points also in the same plane, then the line has to be in that plane. So again, it makes sense, right, if you kind of walk it through it. But so they're just kind of adding or putting together a couple different postulates. They're probably putting together the line postulate about the 2 points, plane postulate with the 3 points, or that three non-collinear points. So notice when they named this plane, they didn't just put the line in here. You have to have 3 separate points that are non-collinear to be able to label a plane. And they also labeled it with R as well. So if you just omitted this F in here, technically that would not be a correct definition or drawing of that particular plane. All right, next one, plane intersection postulate. 2 planes intersect, then their intersection is a line. So again, remember that planes are infinite. So think of like 2 pieces of paper kind of, meshing together. This intersection is not a segment, right? It is infinite. It goes on forever in both directions. So it has to be a line. So if the question were to ask you, name the intersection of these 2 planes, plane S and plane T, you would say it's line L. So it has to be a line, not a line segment, not a ray, because it goes on infinitely in both directions. Okay, so I want to give an example of just something that you might see on kind of your homework or what we're going to be doing in class and so forth. So I'm going to write it down, and you're welcome to write down this example in your notes as well. It should fit okay right here. So sketch a diagram. So this is kind of how we'll be able to assess kind of how like vocab and so forth. So sketch a diagram showing ray Vx intersecting line UW at V, which means point V because it's a capital letter, so that ray Vx is perpendicular to line UW and points U, V, and W are collinear. All right, so why I'm giving you this one is because this is kind of a combo problem, right? It has tons of vocab. So we have to understand what a ray is and understand that this means ray intersects at a line. So again, how we're going to draw that. There's a point, another ray perpendicular to this line, and that has to be collinear. So what I did is I started kind of with the end, and I said U, V, and W have to be collinear. So U, V, W, U, V, W. So if they're collinear, there has to be a line that goes through them. So collinear, great. And so then we can call this line, so UW is the name of this line, right? I could call this UW, I could call this WU, I could call this line VW, there's a few different options here. But this UW is actually referring to this line here. So then it says ray Vx. So again, whenever I give you like letters like this, you wouldn't ever draw like 2 V's on a diagram. What that means is you're going to be using the same V. So like for example here, I want ray Vx. Ray means it has an endpoint and extends in one direction. So it could go diagonally, straight up, whatever, down. It says at V, so that Vx is perpendicular to this line. So I need to put Vx, which means I need to have a point there. And in order for me to show that it's perpendicular, I need to include that little symbol. So if I were to grade you on this, right? So I would be checking, does U, V, and W, are they all collinear? Did you make a line through them? In other words, did you extend? Did you put the arrows? Did you have ray? So again, you did not extend this through, because this is a ray, so there's an endpoint, which means that doesn't extend through, and it goes up forever. Or I guess technically you could have moved it, you could have had it pointing down, doesn't really matter. But did you put point X on there because you needed to have ray Vx? And then also, did you include that perpendicular sign? So again, all of these are, this is just kind of a way for us to interpret how do we do all this kind of like vocab and stuff and to kind of make it into one diagram. All right, so what I'm going to do is I'm going to go through a couple examples on this page, and then I'm going to have you guys pause the video and try the rest of them, and then I'm going to go through the answers, and then that way you can check your work. So let me try these last 2 problems, or these on the page 47. So this is what you're having to do. It says, in exercises 1 and 2, state the postulate illustrated by the diagram. So this is how we kind of read it. If we have 3 points, then we have a line. So what you're going to do is you're going to go back. I'm going to pull up my other sheet here. And we're going to look about which one of these postulates do you think they're talking about. So basically I'm saying if I have some points, I have a line. So the only thing, I don't have anything that says I have a 3-point postulate, but it's talking about a plane. So it says here, if you read the 2-point postulate, through any 2 points, there exists exactly one line. Well, that one would actually work here because even though I have 2 points or 3 points, I only need 2 points to make a line. So technically any of these 2 points, and if I extend it, would encompass all 3 of those points. So the postulate we're talking about here is 2.1, which is the 2-point postulate. So we're just kind of making sure that you recognize which postulate goes with which. So then I want to interpret this one. So it says if, and what this is a picture of is plane. So if I have a plane with 3 points on it, or plane S, then there's a line in the plane. So I think what this one is talking about, so look at all of your postulates that deal with planes. And so the one that kind of talks about a line on here would be the plane line postulate. So if 2 points lie in a plane, then the line containing them lies in the plane. So if 2 points lie in a plane, then the line containing them lies in the plane. So I think that's what this one is, right? So if I have at least 2 points that lies in a plane, then the line containing those 2 points, so M and N, would have to be in that plane as well. So I would call this 2.6 plane line postulate. All right, what I'd like you to do right now is I'd like you to go ahead and try page 48 on your own. And I know that obviously this is a video, and so you're, I'm asking you to kind of, pause the video and do the rest. When you're done with those, I'd like you to unpause, and then I'm going to walk you through all the answers. So please pause now and do the questions. All right, welcome back. So anyway, what we're doing here is kind of the opposite. It says, use the diagram to write an example of the postulate. So 2-point postulate. The 2-point postulate just says, through any 2 points, there exists exactly one line. So on this one, what I'm asking you to do is, through any 2 points, there exists exactly one line. So I'm just going to find a line that has 2 points on it. So I'm going to say line BC. So through any 2 points, there exists exactly one line. Perfect. That's an example of that postulate. The line point postulate. So if I look at my paper, the line point postulate says a line contains at least 2 points. So you could say line BC here contains point. So line BC contains points B and C. We have kind of 2 options here. For the first one, I would have also accepted, I forgot to mention this, line L, because technically you can also name this line L. The next one says plane point postulate. The plane point postulate says a plane contains at least 3 non-collinear points. So I got to find a plane that has 3 non-collinear points, and it looks like plane P is the one I'm going to go with. So plane P is this one up here. It has points A, B, and C that are non-collinear. The plane intersection postulate. The plane intersection postulate states that if 2 planes intersect, then their intersection is a line. So here is this plane, here's this plane. It's almost like they're being folded. Where they intersect is line K. So I'm just going to write plane P and plane Q intersect at line K. All right, next one says RS bisects, so now you're drawing a diagram. Line segment RS, no, I'm sorry, that's, yes, line segment RS bisecting line segment KL. So line segment RS bisecting line segment KL. So it has to bisect KL. So here's K, here's L. Oops, I did that one wrong because it has to bisect at point R. Let me try this again. So what I'm going to have here is, I'm going to have K and L, so there's my line, and RS is bisecting at point R. So R has to be the midpoint. So it looks like this. And then you have to mark those two things as congruent. AB in plane U intersecting line CD at point E and point C not on the plane. So what I did is I drew a plane and I put line AB on the plane. I'm gonna grab a different pen. So line AB, okay? And then it says it intersects in plane U, so I'm gonna call this plane U, intersecting line segment CD. So or line CD. So what I'm doing here, and it intersects at point E. So what I'm trying to show you here is that it intersects through the plane, kind of like up and down. So this is point E, and this is line CD. And then point C is not on the plane because point C is on its own plane above, kind of hovering above. That one's a hard one. All right, the answer's here. I'm gonna go quickly because I have to get to my next class. So plane A and B intersect at line EF. The answer is yes. Points C and D are collinear. I have yes. HJ, looks like ray HJ and line I are perpendicular. And that one is yes. GD is a bisector of EF at point D, and I have yes. IH is congruent to HG, and I have no. And then these two angles are complementary. I said yes. Again, what you have to make sure is that the labels are there and that you know that these statements are true. All right, thanks everyone for joining me today. And if you have any questions, bring them to class, and we'll see you next time. Bye.